Hello, everyone. In the past, we gave you a short journey through the fan aerodynamics. Florian did explain some things about the fan aerodynamics in a past webinar. And due to the good feedback during this webinar, we like to welcome you today to the next webinar, which has the topic TLT-Turbo's Aero Consulting. Florian will show some things about how TLT can optimize fans and the flow conditions in power plants and industrial applications. And I think at the end he will give us an overview of a case study of a retrofit in a waste gas fan in a German power plant. So Florian, good luck, and it's a pleasure to present this webinar. Thank you.
Thank you, Patrick. Yeah, welcome everybody to this webinar, which has the topic TLT-Turbo Aero Consulting. So it's about optimizing fans and flow conditions in industrial applications, all with the goal to save energy and resources, improve reliability, and of course, take a further step into sustainability with TLT-Turbo. My name is Florian Neff. I'm responsible for aerodynamics and acoustics here in the headquarters in Zweibrücken, Germany. And yeah, I have the pleasure to present you this webinar. Let's have a look at the agenda. So we start with, okay, what does Aero Consulting mean to TLT? Why is it a good idea to get consulted with or in aerodynamic questions? What does TLT-Turbo offer, and why should you choose TLT? Then I would like to show you some of our capabilities with which we can consult you. And as Patrick just mentioned, at the end, I would like to present a short case, use case, where we optimized an induced draft fan in a German power plant. And yeah, last but not least, I'll give you a short overview of a typical workflow, how Aero Consulting would work with TLT. Okay, so let's start. What does Aero Consulting mean to TLT? Well, we strive to a holistic approach and do a holistic analysis and consult you on all the aerodynamic topics, especially of course for industrial plants with fans. Because fans, we as a fan manufacturer, we know very much about fans and fan aerodynamics. The main goal is always to identify, of course, potential improvements in your plant, with a focus on energy savings, which correlates, of course, with cost savings in your pocket. And fan reliability improvement is as well an important goal here. And we try to do all this. We strive to propose you a solution which is easy to implement and with rather low costs, so that you have a short payback period. So return of invest is rather short. Why Aero Consulting? Well, as I just said, improved performance is correlated directly, in our opinion, with cost savings. So you can either get higher energy yield if you improve, for example, fan efficiency, or you have a higher yield with lower energy input power. Typically, this can be achieved via three different things. First is, of course, reduction of system pressure losses. So every pressure loss which can be reduced in your plant is correlated with shaft power savings. We can, of course, also have a look at the operational mode of the fan and try to optimize that. And last but not least, of course, we can optimize the fan itself. So what does TLT offer here? Of course, we start with the analysis of your current situation, of the current operational situation. How does the ductwork look like? How do the fans operate? We can do an optimization of the flow and the fan, of course. We could start here with an on-site measurement. So we experienced field service teams come to you, to your plant, and perform on-site measurements in order to get, for example, the current operational conditions of the fan. We, of course, can do analytical calculations, CFD calculations, and we have the capability of conducting full-size measurements or model measurements in our test facilities. And last but not least, if, for example, some measures have been implemented, we can validate them with in situ performance measurements. We also have, of course, experienced engineers and the field service team, as I mentioned, which can help you to execute the improvements on site. So why is it now a good idea to do Aero Consulting with TLT-Turbo? I think you may have heard of CFD suppliers, CFD consultants. There are lots of them on the market. So why TLT? I think I mentioned it several times now. We strive to take a holistic approach here. So we are not only a CFD supplier or consultant, but we have also experience, or we are an experienced manufacturer of fans and the related ductwork. So we go beyond this CFD consultant, and of course we have a competent aerodynamic specialist team and a field service team who can help you to support you in the execution for possible improvements on site in your plant. Okay, now I would like you to participate in a small survey. So this should appear now on the screen in a moment, so that we get an idea of some Aero Consulting questions. So the first question is, do you think energy savings are possible in your facility? And if yes, in what order of magnitude? So we would appreciate if you participate. Okay, the answers popping in. Okay, so most of you think that there might be possible energy savings. So only 8% think no, rather not. But that's good news for TLT. Next question is, by when do you want or need to save energy, for example, due to some mandated legislation? Okay, so similar to the first question, there might be some work needed in the near future. So immediately, or 70% almost within the next 2 years. That's shows us, so thank you very much for participating here, shows us that this topic is a current and crucial one. And I will have another question just in a few minutes, so thank you very much so far. I would like to proceed now and give you an overview of our capabilities. Of course, CFD is a huge part here. So I give you an overview. On the left hand side, on the bottom, you see two pictures where there's a comparison of two ducts connected to two fans on the pressure side in a power plant. So induced draft fans, I think it was. And the customer had asked us to analyze the flow conditions in the duct using CFD as well as to reduce pressure losses if possible. So unfortunately, it must be said that we did not have very many degrees of freedom to change the duct, because it was lots of the work has been done already. But nevertheless, we managed to reduce the pressure losses in the short piece of duct by about 120 Pascal. So this is resulted in this operating point in about 175 kilowatts less drive power at this operating point. So on the left one, with the blue frame here, you see the original configuration. On the right hand side, the optimized with, once again, very low degrees of freedom here. So what we did, for example, which had a huge impact, was to put here tail cone on the hub diffuser, so that the first 90-degree bend was the inflow conditions were better. So once again, it's still not perfect here, the optimized duct. If you have a look at the outlet domain here, the velocity distribution is much more homogeneous. It's still not perfect, but it's more homogeneous. So we maybe also improved the duct system downstream and saved some more energy there. So that the improvement, of course, always correlates to then lowering the resistance lines. On the right hand side, you see typically resistance lines in technical plants, so volume flow and pressure rise on the y-axis. And if you reduce pressure losses, your resistance curve gets lower, and of course that results also with changed operating points for the fan. Okay, another topic where we use CFD is, you see an example where we get asked by a customer to exchange the impeller of a centrifugal fan, because the customer was asking for 20% higher pressure rise. So we performed their CFD calculation of our TLT rotor in an existing foreign housing, fan housing, and yeah, we could achieve this 20% higher pressure, and efficiency should not drop. That was also fulfilled, if not a little bit better at the end. So that's another topic where we use CFD. Of course, we are also using it for optimizing or simulating the flow inside the fan stage, so rotor and stator or guide vanes, or in the components which belong to the fan, such as, for example, the suction box. So on the right hand side, you see before and after plot of the inflow conditions to the fan plates after the flow was flowing, of course, to the suction box. So this improvement does not only improve the pressure loss of the suction box, but also maybe improves the inflow conditions to the blade, and therefore the blades can work as they should. Then I would like to present you some, I would say, special calculations to improve reliability. So here we were asked to have a look at a bearing and the heat transfer on the bearing. So we performed the fluid structured coupling to simulate the heat transfer. So here you can see the two bearings which produce some heat, and the task was to find out whether they got too hot or not, and how we could cool them directly or indirectly. And on the right hand side, we are also capable of predicting where is erosion maybe a factor in the centrifugal impeller here, and where is it necessary to put some wear protection on the plates. Another important thing is we have a 1D solver, so with which we can simulate flow and thermal, the flow and thermal behavior of your system. We can also optimize the operational modes of fans in the system. So here on the bottom left, or on the bottom, you see a picture where we have 6 fans running in parallel mode, and that may cause some problems, especially during the startup phase. And to make it not that complicated, I would like to show you a short video here of a transient simulation. So we have here now not 6 but 2 fans running in parallel, and on the right hand side you see the characteristic diagram of the fans. So it's 2 similar fans, volume flow and pressurized, and these different curves represent different fan speeds. Now you see there's a blue and a red dot. These represent the operating conditions of fan 1 and fan 2. And now we simulated here what happens if, for example, one fan, in this case the red one, is ramping up not simultaneously with the blue one. And unfortunately, it is now here in stall conditions. So that's not a stable and wanted condition for the fan, whereas the blue one is operating as it should. Now, this should be avoided, of course. So there's now some adjustments done with respect to speed in order to get the red fan out of the stall condition. And now they are more or less simultaneously ramping up. And yeah, with this simulation, we could have an idea what are the issues by ramping up 2 fans running in parallel mode, and how problems could be solved. Okay, I don't think we have to watch the video to the end. Now, yeah, both fans ramp up to their designed speed. So it's now once again time for one small survey here. So the question is, what experience do you have with aerodynamic consulting? So that we have a better idea and understanding if you have been in touch with this topic in the past. Okay, seems as if most of you, or only a few, have had already contact with this topic. so 50% none, and for example 25% have implemented measures, but the results were not satisfying. So yeah, thank you very much for participating once again. I think I come to this topic at the end, of course, how the typical workflow looks like, but if you're still interested in Aero Consulting with TLT, so get in touch with us. I'll give you more information about that at the end. So now I would like to show you some more capabilities. Now it's about not CFD, but about aerodynamic test rigs. So we have lots of aerodynamic test stands all over the world, and here we start with presenting you two axial fan test stands with a diameter of 500 millimeters and a drive power of 30 kilowatts. So they are both in accordance with the common international standard 5801. You have also for centrifugal fans a separate test facility here where we can test centrifugal fans up to power of 64 kilowatts. So it's all model size, of course, and that's also in accordance with the 5801. Next slide, we are getting a little bit bigger now. We have another test stand here for axial fans in the power plant configuration here shown with a drive power up to 350 kilowatts, and the diameter of the fan is 1 meter. And that's now in accordance with the American standard 210. Then we have also full-size performance test stands here for axial and centrifugal fans in Bad Hersfeld now, and also in Germany in accordance with the 5801 standard, and drive power is 400 and 500 kilowatts respectively. Last but not least, we also have in Akron, Ohio, so in the United States, here in full-size performance test stand, where we can test axial fans up to a diameter of 2.5 meters, and the drive power is here 400 kilowatts. The biggest one is here in China, in Chengdu, where the motor has a rated power of 6 megawatts, and we can perform here for axial fans aerodynamic tests with a diameter up to 5 meters, basically to every standard you're looking for. And yeah, should also be mentioned the jet fan test stand here in Saarbrücken, where we can test jet fans. So of course these test stands are a good option to not only during the optimization phase, but also to validate the results if we, for example, optimize the fan, so that we can show and prove to you the improvements aerodynamically with some model measurements, for example. Okay, now it's time to show you a current use case. So we did a retrofit here of the exhaust gas fans here in a power plant in Germany. So the operating conditions of the fans have changed, and the initial design of the operating points have changed. So the operating points here in the performance diagram, they are now located in areas with I would say bad efficiency. So we did aerodynamic optimization of the fan and adopted the fan, of course, and figured out how to improve the efficiency values of the operating points here by optimizing the fan. The result have been, depending on the operating point, of course, that we could reduce the power consumption by quite a bit. So 460 and up to almost 1 megawatt in shaft power savings. And depending now on the energy price you calculate, and of course the proportion of operating hours in each operating point, that of course could be 200 up to 450,000 euros a year. Before I show you what we did, let's have a look at some data of the fans. So once again, it was a coal-fired power plant here in Germany, and last year we did here an aerodynamical optimization of these two fans because they had new operating points. One ID fan, or each ID fan, had a diameter of 4.7 meters and 11 megawatts drive power. Each fan consists of 2 stages with 22 blades and 31 guide vanes at each stage. And now the goal was, of course, to optimize the fan so that the operating points have better efficiency and the customer is saving energy and therefore some money. The boundary conditions were, of course, quite challenging because the fan must remain, so we could not replace the fan. So the outer shell at least should remain the same, as well as the rotor, and modification costs should be, of course, as low as possible so that the execution could be easily done within a regular maintenance stop. And our tools here were the model test stand I just presented to you, and of course CMD simulation. So we started in the first step. Due to the reduced operating points with respect to pressure rise, of course, what is the first thing you normally do of the fan in order to get lower pressure rise? You can move out some blades. So we carried out here several model measurements with different variants by reducing the pressure increase here. And now by cutting the number of blades in half, the pressure, of course, significantly dropped. But as you can see here on the far right-hand side, there's at least one operating point which cannot be operated because it's above the store line, and overall the efficiency values and the shape of the characteristic diagram is not very nice and suitable. So we had to perform an optimization of the guide vanes. So the second step was now CFD related. And you can see here on the right hand side, so that's the section through the rotor blade, and that's a section through the guide vane. And you see here the poor inflow conditions and flow conditions around the guide vanes. So there's a huge flow separation, which causes, of course, pressure losses and efficiency. So we did here's different guide vane variants, and also with different numbers. So finally, we also cut here the number of guide vanes into half. So we reduced from 31 guide vanes to 16. And last but not least, we also had to adjust here the leading edge angle so that the flow conditions were improved. Advantage is, of course, the guide vanes can be cut out of the fan housing quite easily. And same applies for the modifications on the leading edge, the guide vanes. And now the last and third step was, of course, a benchmark measurement at our model test rig. So we came here with reduced blades, now did the guide vane optimization, and could catch this operating point here on the far right. So all operating points are now can be operated in a stable mode, and efficiency compared to the original fan configuration was improved. I show you that on the next slide. So we started here with 2 times 22 blades and 31 guide vanes, and we ended up with 2 times 11 blades and 16 guide vanes, but also not only reduced number of guide vanes, also adjusted guide vanes at the leading edge. So having a look at the operating conditions and the operating points now. If we, for example, pick us this operating point here, which is circled in purple, there were the smallest efficiency increase with about 8 percentage points. So now the shaft power dropped from 5,000 kilowatts to 4,450. So more than 450 kilowatts in saving. And for the other operating point here on the bottom, the green one, there have been the largest efficiency increase with 17 percentage points, where we could save almost 1 megawatt drive power. So depending now on the energy prices, so the European Energy Exchange, I hope you can see that on your screen. It's a little bit small, but of course you all may have recognized that the energy prices are rising and rising. So you can sell now your megawatt hour in Europe, at least for, I think in September it was more than 400 euros. So assuming now for these 2 operating points, the green and the purple one, now only I would say 200 euros per megawatt hour. And if you assume, for example, 25% of that of load proportion in that operating point, you would result in 200,000 euros savings a year for the purple operating point, and for the green one, more than 430,000 euros. You can do your own math, of course, assuming another price for energy costs or another proportion of operating hours per year in this operating point, and you will result in the money savings per year accordingly. Okay. Last but not least, I would like to show you how a normal or typical workflow would look like. If you would like to proceed with us in respect to aerodynamic consulting. So how can you save money with TLT-Turbo? Well, of course, you have to get in touch with us. So contact your local sales manager, or go to the website of TLT-Turbo, or write an email to service@tlt-turbo.com. Of course, then we will have a look together on the current situation for free, without any charge. And of course, there's some technical information needed so that we can analyze your situation. We can then propose several concepts and prepare a quotation of our consulting measures. And during the execution, of course, we then would identify potential improvements, present the results to you, discuss it with you, and of course, you can decide and select the optimization measure you would like to implement. And of course, once again, we are not only a CFD supplier, we are an OEM, so we will also do proposal for implementation and support you in your power plant to execute the optimization measures. Okay. Thank you very much so far. I think now it's time to get your questions into here. And if you have questions, I think you can write them in the chat, or I don't know whether it's possible to listen to. Okay, I just heard, please write your questions in the chat, and Patrick will join me now and ask me some questions, or your questions.
Yeah, thanks, Florian, for the nice presentation. It was very impressive. Yeah, during the presentation, we get some questions. The first one was regarding the motors. If the fan is optimized, what means that for the operation of the motor?
Yeah, so the motor, of course, has to be considered. So it may be that due to a new fan design or optimized operating conditions, the motor is not operating in an efficient way anymore because the shaft power decreases so much. So we have to consider the motor, and depending on the motor and of course the situation, there might be some reconstruction of the motor or exchange of the motor necessary in order to get all the benefits of aerodynamic improvements.
Okay, thanks. Then there was a second question. The question was, does TLT adjust the flow guide itself, or how does it work typically?
Normally, I would say yes and no. So we will not execute the works by our own people, but we will send experienced supervisors to your plant in order to fulfill or to execute the work.
Okay, then there's just coming in another question regarding about the test 5802 and the correlation to the CFD. What is experience, e.g. the ID fan for the power plant? So can you answer that?
Of course, I would always prefer to do measurements. You have to consider the background of the measurements, what is possible, what is not possible to measure. So benchmark for me would always be in situ measurements according to ISO 5802 or model measurements. The CFD is, of course, a good tool in order to distinguish which measure will work and what is the expected gain of, for example, pressure loss reduction or efficiency increase. Yes, we have. To answer this question maybe as well in this direction, we have experience by correlating or comparing the CFD results with measurement results. We know where the strengths and weaknesses of the CFDs is, and if you know that, you know how to deal with it. But once again, at the end of the day, I would always prefer measurement. And of course, the measurement at your currency meter is the current meter.
Yes, at the end, this is what counts.
What counts. Yes.
Okay. Okay. Then, how is it in Asia and Japan with these experiences?
So we had some aerodynamic consulting, not in in Japan, I would say, but in the southeast of Asia, we did here several CFD analysis I can remember.
Okay.
So we had experience here.
Yeah, thanks. Another question was, do we have experience with the exchange of centrifugal fans? You mentioned this case study in your presentation.
Yeah, exactly. So there was one slide where we exchanged the impeller and could show to the customer that we fulfill his requirement with respect that he needs 20% more pressure-wise. Excuse me. But I can also remember at least 2, 3, or 5 simulations where we simulated centrifugal fans with respect to exchange.
Yeah, maybe I can add as well. Currently, we are doing some CFD works for centrifugal fans in the mining application in Australia. There, the main topic is wear protection. So we are also capable to do things like that in every application, every industry. So
we also have right now a project running in Germany where we predict wear in the centrifugal fan.
Yeah, okay, yeah, right. Okay, so if you have some additional questions in the future or even today, just contact us. My name is Patrick, product manager for service and aftermarket sales. And if you are interested in some further content, just go on our website. There you will find some additional webinars regarding wear protection, regarding remote service support, and also the webinar I did mention at the beginning, where Florian did talk about the fan aerodynamics. And as well, you will find there some short videos for other products from TLT. And just contact us and we try to help you in your case. Yeah.
Thank you very much.
Thank you very much. It was a pleasure.
Looking forward.